Welcome to AI Paper Podcasts, your shortcut to the latest in AI research. Today, we're diving into, well, a really fascinating paper.
It's called Reinforcement Learning for Reasoning in Large Language Models with One Training Example.
And the hook is pretty incredible, isn't it? The idea that reinforcement learning, RLVR specifically, can get LLMs to state-of-the-art math performance.
Using just one training example, that's the really wild part.
Exactly. So for the quick summary, this paper shows one example can basically match the performance of thousands.
And they saw this across different models, different RL algorithms too.
Yeah, and it leads to some strange, interesting effects like post-saturation generalization and more self-reflection from the model.
And the key driver seems to be the policy gradient loss, not what you might typically expect.
So stick with us as we unpack how this works and why it's, frankly, challenging a lot of assumptions about needing massive data sets.
It really is. We're talking about reinforcement learning with verifiable reward RLVR. It's already known to be pretty good for boosting reasoning, especially math.
Right. People often focus on tweaking the algorithms, making the RL process itself better.
But this paper asks a different question, a really fundamental one about the data. How little do you actually need?
Yeah, we're all sort of conditioned to think bigger is better for data sets, always more data.
But maybe not always. They wanted to see just how far they could push it, how much they could shrink that training set for RLVR in math reasoning without losing performance.
And the results are, well, kind of mind-blowing.
Astonishing, yeah. They showed that with just one carefully picked example, you could match, sometimes even beat, what you get from data sets with, like, over 1,000 examples.
Think about the implications there, especially if you're constrained by data or compute, which, let's face it, many are.
Definitely. So today, we'll dig into this one-shot RLVR result.
We'll look at those magic examples they found, Pi1 and Pi13.
And that weird post-saturation generalization thing, where it keeps learning after it seems like it should be done.
Plus the self-reflection aspect and how the model seems to think more carefully.
We'll also touch on the mechanisms, policy gradient, entropy loss, and check how robust this is across different setups. Let's get into it.
Okay, so the core finding. They took Qwen 2.5, Math 1.5b.
Right, a 1.5 billion parameter model focused on math.
And they applied RLVR using just one single math problem for training. The whole data set was one problem.
And the performance jump was huge. On Math 500, accuracy went from 36%,
which is okay, but not amazing,
to 73.6%, a massive leap.
73.6, with one example, that's nearing top-tier performance. It just, well, it goes against everything you'd intuitively think about training data.
And it wasn't just Math 500. They looked at 6 math benchmarks overall. The average score basically doubled, went from about 17.6% up to 35.7%.
Okay, but here's the kicker, right? That 35.7% average.
It matched the performance they got when they used a 1,200 example data set, and that bigger data set included the single example they tested.
So the other 11,199 examples didn't really add much beyond what that one specific example could do.
Apparently not, in terms of the final average performance. And get this. Using just 2 examples, actually did slightly better than the 1.2K set.
Okay, that's just wild. So more isn't always better here. Maybe redundancy kicks in quickly.
It really makes you question things. And it wasn't a fluke with just that one model either.
Right, you mentioned other models.
Yeah, they tried the bigger Qwen 2.5, Math 7b, Llama 3.2, Dwash 3b Instruct, even a distilled model, DeepSeek R1. Saw similar patterns.
And different RL algorithms, too, not just their specific RLVR setup.
Correct. They showed it worked with PPO as well, similar improvements with just one example.
So it seems pretty general. What about the examples themselves? Were they special?
Well, they tested many different math problems as a single training example. A lot of them gave a boost of around 30% or more on Math 500. So it wasn't like only 1 or 2 magic problems worked. It seems like many problems have this potential.
Okay, but they did highlight 2 specific ones, 1 and 13. What were they?
Let's take 1. It's an algebra problem, but with a physics flavor. Wind pressure on a sail. You need to find the wind velocity.
Okay. Anything unusual about it?
Kind of. The ground truth answer given in the data set was 12.8.
Yeah.
But if you calculate it precisely, it's more like 12.7.
A slight inaccuracy. Interesting. And could the base model handle this before the RLVR training?
That's a key point. The base Qwen model could already do most of the steps needed for one pretty well.
So it wasn't learning from scratch?
No. The main place it tripped up initially was the very last step, calculating a cube root. It would sometimes get 12.8, sometimes 12.7, sometimes other close values.
Got it. So the foundation was there. What about 13?
Pi 13 is geometry. Finding the equation of a circle through 3 points, then finding words for a line intersecting it. More complex, maybe.
And the answer?
Precise numerical answer for this one. And again, like 1, the base model wasn't completely lost. It actually got the final answer right a fair amount of the time, even before RLVR.
So these magic examples weren't necessarily super hard problems the model had never seen. They were problems that kind of sort of knew how to do already.
Exactly. Which makes what happens next even more interesting. The training process itself.
Right, this post-saturation generalization thing you mentioned.
Yeah, so you're training on just one example. The model learns it super fast. Accuracy on that specific problem hits 100%, maybe in the first 100 steps.
Which is when you'd normally think, okay, training's done, anymore is just overfitting.
That's the standard playbook, yeah.
Yeah.
You'd expect performance on new, unseen problems, the test set to level off or even drop.
But that's not what happened.
Not at all. Even after the model totally nailed the training example, its performance on the general math benchmarks kept climbing significantly.
How significantly?
With 1, the average test score improved by another 3.4% between step 100 and step 1540, long after it had already learned 1 itself.
Wow.
And with 13, it was even more dramatic, a 9.9% average gain on the test sets between step 500 and step 2000.
That's amazing. It's like perfecting that one example somehow unlocks broader skills, even much later.
It seems that way. And it's the opposite of what they usually see with bigger data sets, where test performance often peaks and dips before the model has even fully memorized the entire training set.
So strange. But then, did it eventually overfit the single example?
Oh, it did, and in a really bizarre way. Very late in training, like way past step 1500 or so.
What happened?
The model's output for that specific training problem, like 1-1, became this super long, rambling mess. Gibberish, multilingual text. Just nonsense.
Seriously?
Yeah. But, crucially, buried within all that nonsense were still the correct steps to solve the problem.
Okay, that's weird. But what about the test problems? Did performance crash then?
Nope. That's the craziest part. Even while it was outputting gibberish for the training example, its performance on the unseen test problems stayed strong. And its reasoning steps for those test problems looked totally normal and logical.
So the overfitting was contained to just that one training example. It didn't poison the well for general reasoning.
Apparently not. And this extreme overfitting happened really late, after millions of training rollouts. It suggests the model somehow separates its handling of the training data point from its general reasoning strategies.
That's, yeah, a really fascinating glimpse into the dynamics. Okay, so it generalizes surprisingly well. You said it generalizes across different types of math problems too.
Absolutely. Training on that one example, say an algebra problem like 1,
didn't just make it better at algebra.
Right. It improved performance across all the categories in Math 500. Algebra, geometry, number theory, pre-calculus, everything got a boost.
So it's not just learning a pattern for one type of problem. It's like it's learning something more fundamental about mathematical reasoning itself.
That seems to be the implication. It's activating a more general capability.
And you mentioned most examples worked to some extent.
Yeah. Almost all the ones they tested gave a decent boost, around 30% or more on Math 500. The only real exceptions were problems where the reward signal was basically absent.
Like if the label was wrong in the data set or the problem was just way too hard for the base model to even get close.
Exactly. If the RL process never gets positive feedback, you can't learn much. Makes sense.
It does. And what about combining examples? Did 2 always beat 1 or 4 beat 2?
Here's another counterintuitive bit. No, combining examples didn't always yield better results. Sometimes, one carefully chosen example actually outperformed a set of several examples.
So quality over quantity, potentially. The specific nature of that first nudge matters more than just adding more nudges.
It seems that way in this one-shot RLVR context, yeah.
Yeah.
And even weirder, training on, say, a geometry problem didn't necessarily give the biggest boost to other geometry problems in the test set.
Huh.
Yeah, you might train on geometry, but see the biggest improvement on number theory test questions, for example.
Okay, that really highlights how complex this learning process is. It's not a simple mapping. What about this self-reflection point?
Right, this is more of a qualitative thing they noticed. As training went on, especially in the later stages, maybe after step 1300 or so,
Yeah.
the model started using phrases like rethink, recheck, recalculate more often in its answers on the test data.
So it seemed to be thinking more carefully. double-checking its work.
Something like that. It suggests a more deliberate reasoning process is emerging. This also happened around the same time the model's answers got longer and the entropy loss metric increased.
Interesting. Was this totally new behavior?
Not entirely. The base model already did some self-reflection, but one-shot RLVR seemed to amplify it.
And how did this compare to training on the big data set?
Interestingly, when they trained on the 1.2K example set, that kind of self-reflection language actually decreased slightly.
Another way the one-shot training seems different. Okay, let's talk versatility. How robust was this across different setups?
Pretty robust, which is important. They had confirmed one-shot, and few-shot worked well on the bigger Quinn 7b model, too.
How well?
The 7b model got nearly an 18% average boost with just one example. And using just 4 examples was enough to match the performance of the full 1.2K dataset for that larger model.
Okay, so it scales up. What about different model families?
They tried Llama 3.23b Instruct. The absolute gains were smaller there, which might be expected depending on the base model's strengths. But again, few-shot RLVR matched or sometimes beat the full dataset training.
And models specifically trained for step-by-step reasoning, like chain-of-thought models.
Ah, yes, the DeepSeek R1 Distill model. That one was interesting. It was already trained on lots of chain-of-thought data.
How did one-shot do there?
It still helped, but the gains were smaller compared to the Quinn models, and they noted some potential instability with just 1 or 4 examples.
Suggesting maybe those heavily pre-trained distilled models need a bit more RL data to adapt stably.
That's the hypothesis, yeah. They might be more set in their ways, so to speak. And finally, they confirmed it wasn't just their specific RLVR algorithm, they swapped in PPO.
Proximal policy optimization, a standard RL algorithm.
Right. And again, one-shot PPO gave significant improvements on the Quinn 1.5b model.
Okay, so the principle seems solid across models and methods, even if the exact benefit varies. So let's get to the why. What's driving this? Policy gradient and entropy loss.
Exactly. They did ablation studies, basically, turning different parts of the learning process on and off to see what matters most.
And the winner was?
Policy gradient loss. That seemed to be the main engine driving the performance improvements in one-shot RLVR.
How is that different from something like Crocking, where models suddenly generalize after seemingly just memorizing?
Crocking often relies heavily on regularization, like weight decay. But here, they found that even without weight decay or other explicit regularizers like KL divergence loss, just optimizing the policy gradient on that single example did most of the heavy lifting.
So it's not just memorization followed by delayed generalization. The learning process itself is different.
It seems so, but they also found that adding entropy loss on top of the policy gradient gave a further boost.
And the thinking there is entropy encourages exploration.
Yeah, exactly. Entropy loss basically penalizes the model for being too certain, pushing it to explore different reasoning paths or strategies. If you only have one example, you need the model to try different things around that example to find generalizable solutions.
That makes intuitive sense. Anchor on the one correct example, but explore around it.
And they found other evidence for exploration being important too, like increasing the softmax temperature during the training rollouts. Another way to make the model's choices more random and exploratory also improved results.
So the hypothesis is policy gradient locks down the correctness for the known example, while entropy loss, or temperature, pushes exploration to find strategies that work more broadly. It acts like an implicit regularizer.
That's the core idea they propose. The policy gradient ensures you get that one problem right, but the exploration finds robust ways of getting there.
Okay. Now, there was that other really weird finding about entropy loss alone.
Ah, yes. This was super surprising. They tried training with only entropy loss. No reward signal at all telling the model if its final answer was right or wrong. Just explore.
And
it still significantly boosted performance. For Quinn 1.5b on Match 500, just adding entropy loss gave a 27% improvement over the base model.
27%, just by telling it to be less certain and explore more without any feedback on correctness.
Yeah. Similar effects on other models, too. It's quite remarkable.
How does that even work?
It's not entirely clear, but it suggests that simply encouraging diverse outputs might push the model to develop better internal representations or reasoning pathways, somehow making it better at solving problems even without direct reward. It's definitely something that needs more research.
Absolutely fascinating. Okay, one last piece. Label correctness. Did that single example need to be perfectly labeled?
They tested this too. They fiddled with the ground truth label, for the single training example.
Did minor errors matter, like that 12.8 versus 12.7 for one?
Minor inaccuracies like that didn't seem to hurt much. The model could still learn effectively.
Well, what if the label was way off?
Here's where it gets nuanced. If the label was substantially wrong, but still something the model could potentially guess or latch onto.
Like a wrong number it could learn to output.
Right. That scenario actually led to worse performance than if the label was completely nonsensical, something the model just couldn't possibly learn to predict.
Wait, so a completely wrong, unlearnable label was better than a significantly wrong but guessable label?
Yes. The completely wrong, unguessable label led to performance similar to just training with entropy loss alone. It seems like a badly wronged, still learnable label can actively mislead the model more than just noise.
That makes sense. A plausible but wrong target is worse than no target at all.
Exactly. So pulling all these threads together, what does it all mean?
Well, it really seems to imply that these base models, even the smaller ones, already have a lot of reasoning ability baked in, doesn't it?
It really does. It suggests the capability is latent, just waiting to be unlocked or activated. And apparently, one-shot RLVR is a surprisingly effective way to do that with minimal data.
So the big takeaway from this paper?
I think it's the incredible data efficiency. The idea that one example can trigger such a massive performance leap in complex reasoning is, well, game-changing. It really forces us to rethink how much data we actually need, at least for this kind of task with RLVR.
It definitely challenges the scale is all you need mantra in a very specific way, and it opens up so many questions, right?
For sure. Like, what makes an example a good igniter for reasoning? Is it about covering certain skills, or being slightly challenging but solvable for the base model?
And what exactly is happening during that post-saturation generalization? How does the model keep improving on test data long after mastering the training data?
Understanding that mechanism better could be huge. And how do we best select these crucial few examples? Is there a science to it beyond just trying them out?
And can we apply this beyond math? To other reasoning tasks, code generation, creative writing?
Big questions. Thankfully, the authors open-sourced their code and models, so the community can jump in and explore.
Which is great. We encourage you, our listeners, definitely check out the paper if this sparks your interest. The links will be available.
It really makes you wonder, doesn't it? Maybe unlocking the next level of AI reasoning isn't just about throwing trillions of data points at models.
Maybe it's more about finding those specific keys, those minimal but potent examples that strategically engage the potential already sitting inside these networks.
A very different approach to consider. Smarter data, not just bigger data.
A provocative thought to end on. Thanks for joining us on AI Paper Podcasts.
Catch you next time.